Assalamualaikum and hi. So this is the third video of force convection internal. So in this video, I'm going to explain the general thermal analysis. General thermal analysis. In the absence of any work interaction, the conservation of energy equation for the steady flow of a fluid in a tube is as shown in this equation, which we get from the energy balance equation of the energy in plus the Q in equal to energy out, and then you can rearrange this equation to be the Q dot, which is the energy in, equal to mass flow rate m dot times the specific heat Cp times the temperature difference between the exit and the inlet. So the thermal conditions at the surface can usually be approximated as constant surface temperature or constant surface heat flux, which I already mentioned in the previous video. The mean fluid temperature Tm must change during heating or cooling. So either the surface temperature is constant or the heat flux at the surface is constant, but we cannot have both at the same time. Two cases in thermal analysis. Case 1, constant surface temperature, Ts equal to constant. And then case 2, constant surface heat flux, Qs equal to constant. Constant surface heat flux, Qs equal to constant as the boundary condition, as I show you in the figure on your right hand side. In the case of constant heat flux, the rate of heat transfer can also be expressed as this equation, which we get from conservation of energy equation for steady flow, which I already showed you in the previous slide. Then the mean fluid temperature at the tube exit becomes, from the equation which I put in the blue rectangular, you can rearrange it to be the exit temperature of the fluid, which I put in the red rectangular. So this is the exit temperature of the fluid. The surface temperature in the case of constant surface heat flux can be determined from convection heat transfer equation. Here H is the convection heat transfer coefficient, Ts is the surface temperature of the tube or pipe, Tm is the mean temperature of the fluid inside it. Then you can rearrange this equation to be the surface temperature as I put in the green rectangular equation. So here we have two kind of temperature, which is the exit temperature of the fluid, and then we have the surface temperature of the tube or pipe. Constant surface heat flux. As you can see on your right hand side, we have a temperature versus distance for boundary condition of Qs equal to constant. We have two lines, black and pink line. Black line is the surface temperature and the pink line is the fluid temperature. In the fully developed region, the surface temperature Ts will also increase linearly in the flow direction. As you can see in the figure on your right hand side, in the fully developed region, the Ts, which is the black line, increase linearly with the distance x. Applying the steady flow energy balance to a tube slice of thickness dx, the slope of the mean fluid temperature Tm can be determined. Here we found that the slope of the pink line is constant, starting from the inlet temperature to the exit temperature. Noting that both the heat flux and coefficient convection H for fully developed flow are constant, we found that both the slope for surface temperature and fluid temperature is constant and equal. Constant surface temperature, Ts equal to constant, is the boundary condition of this system. Rate of heat transfer to or from a fluid flowing in a tube is given by this equation, which is the convection heat transfer equation. Here H is the convection coefficient. AS is the surface area, delta T is the average temperature, which is given here as the surface temperature minus the mean temperature of the fluid. There are two suitable ways of expressing delta T average. One is arithmetic mean temperature difference, and the second one is the logarithmic mean temperature difference. Now we look into the arithmetic mean temperature difference, which is given here as delta T inlet plus delta T exit. So divide by 2, and the delta T inlet given here as the surface temperature minus temperature inlet, whereas delta T exit is the surface temperature minus temperature exit. So from this expansion of temperature, we can rearrange it to PV, surface temperature minus TB. PB here is the bulk mean fluid temperature, which I already explained in the previous video, and it is given here as PB equal to average of the inlet and exit temperature. Okay, there is a note here. By using arithmetic mean temperature difference, we assume that the mean fluid temperature varies linearly along the tube, which is hardly ever the case when surface temperature Ts is constant. This simple approximation often gives acceptable results, but not always. Therefore, we need a better way to evaluate delta T average. Constant surface temperature. So there is a figure of temperature versus distance x for constant temperature boundary condition, and then the black line is the is referring to the constant surface temperature, and then the pink line is the temperature of the fluid from the inlet to the exit. So from this relation, which we get from any distance dx in the tube, so this which I put in the red rectangular, we can expand it to be equation in the black rectangular, whereas dAs we can expand it into perimeter times d dx, and then we can rearrange this equation to be d delta temperature surface minus mean temperature of the fluid divided by surface temperature minus mean temperature equal to minus h convection coefficient times perimeter divided by mass flow rate m dot times specific heat Cp times dx. If we integrate this equation from x equal to 0, which is the tube inlet, and the mean temperature of the fluid is equal to inlet temperature, to x equal to n, which is the maximum distance or maximum length of the tube or pipe, which is the tube exit, and the mean temperature of the fluid is equal to the exit temperature. Then we get this equation, one equation from the integration, and if we rearrange this equation, we can calculate the exit temperature of the fluid, which I put in the red rectangular equation. I will explain this equation which related to NTU in the next slide. And if we solve this equation, we can get the relation of mass flow rate m dot times specific heat Cp, which equal to this equation, which I put in the blue rectangular equation. And from the general thermal analysis equation, which I put in the pink color equation, we can replace the mass flow rate m dot times specific heat to this equation, and then we can get this equation, which is similar to the convection heat transfer equation. And here you can see H is the convection coefficient, AS is the surface area, and then we have this delta T ln ln. Delta T ln here, the expansion is this equation, which I put in the black color rectangular, and this is the log mean temperature difference. Constant surface temperature. So exit temperature, this is the exit temperature relation which we get from the previous slide. And here the convection coefficient times surface area divided by mass flow rate and the times Cp specific heat is equal to NTU. NTU here is the number of transfer units, a measure of the effectiveness of the heat transfer systems. For NTU equal to 5, the exit temperature is equal to the surface temperature and the limit for heat transfer is reached. And as you can see on your right hand side, there is a figure and table for NTU and also exit temperature, which is the effectiveness of the heat transfer. And as you can see here, when the NTU is 0.01, the effectiveness is 20.8. Whereas when the NTU equal to 5, the effectiveness is 99.5%. And if you increase larger than that of the NTU value, you only get 100%, which is the maximum of it. So delta T ln, which is the log mean temperature difference, is an exact representation of the average temperature difference between the fluid and the surface. So we have two temperatures here. One is the surface temperature and the other one is the fluid temperature. So large NTU value, increasing tube length marginally increases heat transfer rate. Meaning that if the NTU is already close to the 5 or larger than 5, then if you increase the tube length, it will increase slightly the heat transfer rate. But if your NTU value, small NTU value, heat transfer increases significantly with increasing tube length. Meaning that if you have a small value of NTU, if you increase the tube length, you can increase significantly the heat transfer rate. So this is the end of third section for post convection internal. So thank you and hope you enjoy